Hi, good evening, Professor Chen.
Hello.
So we are 1 minute away. Uh, the TA in the classroom, are the students ready? Okay, great. So today we have Omey. I hope I didn't mispronounce your name, Omey
That's exactly
Manyar.
right. Yeah.
So he will be presenting a presentation entitled "Learning Manipulation of Deformable Objects: A Physics-Informed AI Perspective." So physics-informed AI is very popular recently. I think this presentation will be very inspiring to the students in the classroom. So I will give the floor to you, Omei.
Sure. Yep. All right. Let me just start presenting my slides, and then I think. Can you see my slides?
Yes, can you try to full screen mode?
Yes. Yes, I'll do that. All right. So
Yes,
I'm assuming my slides are getting projected, and if I'm good to go, then I can start the presentation. All right, I'll take that as a yes. So, well, hello everyone. My name is Omey. I'm a fourth year PhD student in the Viterbi School of Engineering at USC, and I work in realization of robotic systems lab, where we mainly focus on using robots for different type of applications, mainly focused in manufacturing. And today I'll be delivering a talk which kind of encompasses my research that I've been doing, where we'll try and see what different types of physics informed learning methods we can use for enabling robots for deformable objects. And what my objective is, what my promise to you is, at the end of this talk, you will walk away with a different set of tools that you can use to integrate intuitive physics with modern data driven machine learning methods such that robots can manipulate complex deformable objects. Now, deformable objects are becoming more and more prevalent across several industries, be it aerospace, where you use composite sheet, fulfillment industry, where earlier where you used to have like a rigid box, now it's turning into more flexible packages, as you see in the video in the middle. And then in the automotive industry, where you have a combination of different type of deformable objects. Now, they're getting more and more integral even in our indoor and outdoor environments. And if we really want to revolutionize human development, we need robots that can possess the ability to kind of intricately and smartly handle these deformable objects. And in addition to that, industry is currently facing severe labor shortage. So kind of that kind of motivates this entire problem to enable robots to perform such manipulation tasks. Now, deformable objects are definitely not easy because, unlike rigid objects, the dynamics is quite complex and it changes based on their size, the material, and the interaction dynamics can be quite complex as well. Now, when we humans perform certain actions, we perceive our surrounding and takes those actions, and we have a very good understanding of the world model. But when it comes to perceiving deformable objects, defining a state so that we can take appropriate actions with the robot becomes quite challenging as well. And throughout these presentations, we'll try and focus on these challenges head on. Now, the overall theme, again, deformable objects and using robots to manipulate deformable objects has been a well-studied topic for in the past decade. So, but most of the prior work, the way they kind of segregate this problem is into three phases. We have a modeling phase where we learn the physics of the object that we are modeling. We have a policy generation phase where we kind of learn the right actions to take such that a task is accomplished. And then there is execution phase where you have different sensing modalities and you get feedback and then you execute the policy resiliently. And we'll look, and the work that I will present today will kind of tap into each of these phases and try and show you how we can perform manipulation planning by tapping into each of these phases. Now, there are two possible approaches that people have taken in the past. One is a pure data driven method where the idea is you collect a bunch of data, be it like demonstrations or in simulation or whatnot, and then just pump it into a model and then let the model do certain type of prediction in a supervised learning way. Then there is a pure physics-based method where you kind of write different type of analytical equations, define how these objects would behave under external forces and constraints. And each of them have their own advantages and disadvantages. Now, in pure physics-based methods, you kind of have this physics engines or like an analytical model that helps you make different type of decisions for policy generation, or you have execution based on feedback mode. Now, there are definitely certain limitations when it comes to having pure physics-based methods. That is, your model is always going to be approximate. And since these are deformable objects that we're dealing with, pure analytical methods always are inaccurate in terms of quantifying the complex physics that they have. And also, they can be sometimes computationally expensive and also slow, and they may not be able to kind of encapsulate the nonlinearities and material interactions. So the natural step would have been like, okay, can we augment these physics-based methods with real-world nonlinearities with the help of data? And that brings us to mainly database methods, where you kind of, in the modeling phase, what you try and do is generate a physics-based simulation where you observe the object deformation under external constraints and try and learn that. Or you use, in policy generation, you use RL-based methods or imitation-based learning methods. And in execution, you kind of do feedback loop control. Now, even a pure data-driven method can have its own disadvantages. Now, although these methods have shown great promise in manipulation, most of these methods are executed in a control environment, and then they face their own set of challenges where, always collecting training data may not be feasible, and training data may not even represent the right physics, which in deep learning community we term as the right inductive bias that is required for the model to generalize. If we use RL-based methods, sim to real gap can be quite detrimental, especially if you're using image-based observation. And pure data-driven models are always going to be black box. That is, for example, when we humans take certain actions in the environment, we kind of have a physical model of the world, that how our actions are going to affect the surrounding. And these black box based models lack that system behavior and makes them inherently unsafe. So in today's presentation, what I will try to give you is a best of both worlds, where we would combine these data-driven and physics-based methods. And what I would like to give you is a certain tools in armamentarium, where we will try and see how we can use simulation, advanced learning frameworks, how to learn physics-informed constraints, and how to do multimodal data fusion in a task-informed manner. And using these methods in a combination is quite important, and how we can solve deformable object manipulation in a smart way is what we'll look at in the presentation. And before I proceed, I want to keep this presentation as interactive as possible. So please feel free to interrupt and ask any questions along the way if you have any. All right. Now, the goal of the work that I've presented is mainly learning how these 4 different methods can help us enable in understanding physics constraints, task-based constraints, and we are mainly interested in using robots for high precision tasks where we routinely encounter them on manufacturing floors. So most of the examples will be derived or motivated in terms of manufacturing and also in terms of fulfillment. And especially when robots are operating in highly unstructured environment. Now, one notion that most of the people have when you talk about manufacturing robotics is that you envision this assembly line where everything is highly structured, and you have this $1 million cell setup with high precision jigs and fixtures to reduce that uncertainty. But nowadays, especially where deformable objects are, you're dealing with deformable objects, these kind of manufacturing settings are high mix, low volume. So you cannot invest millions of dollars in buying these jigs and fixtures. And that is why manufacturing environment which involves such deformable objects is still considered as unstructured environment. And then in addition to that, your robots need to be smart. They need to be resilient and they need to predict failures and also need to learn how to recover from them. And specifically, we are going to talk about scenarios where data is limited, your state uncertainty is high, and your failures can be detrimental, which is most of the manufacturing applications in aerospace and any of the high performing sectors. Now, before we proceed, let me motivate you how my entire research journey began from a real world application that we studied in a multi robot cell. Over here, what we're doing is we're doing composite sheet layup, and you can see one robot picks and drops the sheet, and the other robots are kind of draping the sheet on top of a tool, while we have a heating robot, which you can see at the leftmost corner. We have multiple, and another robot which supports the sheet and manipulates it such that it is placed in the right environment. Now you can see, even though this task looks simple where you're placing like a sheet, there are a lot of tasks that are involved. And to actually take care of each and every task such that everything is, executed seamlessly, we need to develop tools in each of those modeling phases and policy generation phase and execution phases I talked about. So let us first take a look as to what we did in modeling phase, where we're trying to model the dynamics of such deformable objects. And what we try to do is, if you can see the image in the left, in real world we have a composite sheet which we're supporting with external constraints. And you have, if you can see, you have markers on top of them. And what we do is we generate like a point cloud or a scan of these images, and then we use machine learning to kind of learn the material parameters of the sheet so that we can generate a physics-based simulation. And what we observed was the error was in centimeter scale, which is good enough for robotic planning. I'm going to go quickly through these initial examples, and I'll delve deep into some other examples which might be more interesting for you. Then the second phase, which is the policy generation phase, is where we try to learn simulation-based grasp planning for deformable objects. And this was presented in ICRA in 2021. Now, the objective over here is you have a manual process where you can see in the leftmost image, where you have two humans performing a complicated task such as composite sheet layup. You have a plan generation phase and you have an execution phase. And what you try and do is, for this composite layup task, you're executing the layup in a sequential manner. And the sequence is which region to process for this big sheet. And for each and every region, you're trying to predict what is the right manipulation pose for the two robots that you see in the image. And that is what we did in that particular paper. And then if you saw the initial video, there was one particular task where you have to pick and place the sheet. Now that demands for online execution control, where you use methods such as traditional control methods such as Visual Servo, but you use modern machine learning methods to do feature extraction and feature determination as to which features used to align for a deformable objects. And in our results, we found that we can achieve a accuracy in placement up to sub-millimeter and sub-degree level. Now I will come to more interesting work which we've been doing recently, which where we truly tap into physics-informed AI stuff. And the first work that I would like to talk about is learning task sequencing policies for manipulation, which was presented at ICRA in 2023. The objective over there was that an expert is performing a composite sheet layup task, and can we kind of learn such useful manipulation strategies from the expert such that a robot given a tool or given a new part of similar complexity can execute without any sort of fine-tuning or pre-training. And that is what our main objective was. And the motivation for this is there are several processes, like I mentioned, which are high mix, low volume and require complex human skills. And most of these traditional methods are still being performed by humans. And humans have a lot of process knowledge which needs to be tapped into. And then we can perform learning from demonstration for such complex tasks. And the example that we're going to study in this specific work is the composite sheet layup example. Now, let us first understand how this composite sheet layup is executed. If you guys see the green highlight that is being happening, that is the specific region or the zone on the tool that is being process. And for you to obtain like a high quality part in composite sheet layer, the sequence matters quite a bit. And there's nothing random in this sequence. It is being carefully sought out for actually avoiding any sort of defects such as wrinkles or air bubbles. That is why you start at the top and then you move towards the edges of the tool so that you can get rid of those air bubbles and sequence. This is what we kind of noticed by observing experts and getting the demonstrations. So then what we wanted to do is we wanted to teach our robots to do this kind of process. There are several potential approaches. You can do heuristic-based approach, but then that is not going to generalize well to different types of new parts. You could do simulation in RL, but when it comes to deformable objects, having a good simulation so that an RL policy can learn something is again quite difficult. And that is why learning from demonstration is quite promising in such kind of manufacturing tasks where you have a lot of process knowledge, you have a human expert that can give you demonstration, and you have a method in which you can capture that information. So I would not go too deep into the problem formulation, but the problem formulation is given a sequence that the expert has demonstrated. Can you learn certain sequences for a given state action pairs and a given feature vector such that the expert demonstrated sequence is indeed the lowest cost sequence? And if you've learned such a weight function or weights, a set of weights for the cost function for a set of tool of similar complexity, then given a new tool, what you can do is you can, let me go back to the initial slide. Given a new tool, you can use the same set of weights to now do forward learning where you're trying to come up with the right sequence in which you need to execute the part. Now the features that you need to select for such a learning methodology is mainly geometrical based features. As I mentioned, that most of the time what experts are doing is they're starting at a region on the mold which is at a higher height, and then moving towards the edge of the tool so that they can get rid of the air bubbles. And then other issue that you can have when you deal with learning from demonstration kind of problems is that you never know that if your demonstration data set is rich enough for you to learn something which is actually generalizable. But the demonstration data that you have and the features that you need to learn kind of give you a good information. So what you can do is you can learn the interactions between these features and actually kind of quantify the feature interactions that you've captured in your demonstration data set. And that tells you whether you're going to learn anything useful out of your demonstration data set or not. And if you find out that the interactions are loosely represented, then you can ask the expert to provide a specific demonstration online. And that way you can keep on enriching your demonstration data set. And what happens in inverse reinforcement learning is that what you're trying to learn is the expert demonstration sequence. But once you've learned certain set of weights, there could be multiple sequences that can give you an optimal kind of output. So that happens mainly when two of the sequences or two of the expert demonstrated sequences have the same type of feature vectors. So then how do you kind of select the right set of weights? That is where in manufacturing setting, you would have to apply for an effort-based preference. For example, in this specific example, you could start processing the tool at, let's say, from region 9 and move towards region 1, 2, 3. Or you could start with region 1, 2, 3 and move towards region 9. But once I give you a constraint that the two robots are closer to region 1 and region 3, you would immediately select a sequence which would start at region 9. And that is how you learn expert performance-based preferences and kind of effort-based preferences, which are more of a function of how your manufacturing cell is laid out. And you select the right set of weights accordingly. And here you can see how the expert is processing the part, and you have multiple robots performing grasp planning, as well as the expert is performing more complex and intricate draping where he's trying to stick the sheet on top of the tool. So overview, just to conclude this specific set of work, you have a demonstration stage, you have a learning stage where you're kind of refining your demonstration data set, and you're learning different expert preferences. And in execution stage, you're trying to execute the policy, and given a new tool of similar complexity, the robot can easily process it and you don't need to collect any more information. I will skip through this and then just show you how exactly we collect the demonstration. You can see that the expert has a handheld tool and there's motion capture information. And the tool is divided into different regions based on the geometrical features. And then we record the expert demonstration and the sequence that the expert is following. And once we have learned the right expert policy, given a new tool and its region definition, we can come up with the right sequence as well as the right trajectory parameters for the robot to execute and perform this kind of task. And you can see this is completely autonomous. Over here, we did not collect any demonstrations on this tool. All we did was, given the expert policy, we kind of see how well the robot did in terms of the expert. And we actually did part verification, and it met the industrial standard that are required for the composite part to be considered a success. And in results, we show a different learning methodology, how it gives you a high quality solution, and how we kind of deconflict if there are two sequences of the same cost sequence. And if you're interested, you can read the paper which was published in ICRA. And the key insights that I would like you to walk away with is that the sequence in which you execute such a manipulation policy also affects the outcome of the entire process. And for doing learning from demonstration or imitation learning, inverse reinforcement learning can serve a very good tool, especially when defining a reward function or extracting the expert's reward function becomes quite complicated. Now, moving to another work that I would like to focus on, where we use physics-informed AI, is when you have to kind of manipulate something complicated in an environment where uncertainty, especially your state uncertainty, is high. And this work was published in IROS in 2023. Now, robots, it's a very well-known fact that robots mainly struggle in unstructured environment. Because what happens is you have uncertainty in your observations, and once you get your observation, your state estimation inherently suffers. And if your state estimation inherently suffers, what that leads to is your policy to give you actions which are suboptimal. And this mainly happens in a lot of maintenance tasks where you have high mix, low volume kind of a setting, and you need high precision. And that is why robots need to operate in such kind of environments where they have high uncertainty and still be able to perform such complicated tasks quite well. And what we found out that in a task such as screw driving, which is quite relevant in assembly kind of tasks, when you have compliance in the robot, which comes in the form of impedance control, and you have compliance in the tool. And if you closely observe the video over here, you can see that the robot, while performing the screw driving action, was quite off. But screw is performing this kind of whirling motion, which leads it to drop inside the hole. And once it's inside the hole and engages, because of the combination of passive compliance of the tool and active compliance of the robot, screw driving can still be performed when you have high state uncertainty. And after this observation, our objective was to study the effect of this compliance on the dynamics of the screw tip. So to define this problem more concretely, you have like an agent, imagine like a mobile manipulator, such as the one shown in the image, which is operating under impedance control, and it's operating under high state uncertainty. And this robot receives certain noisy observations. In this case, it was image and force information. Can you still perform a complicated task such as screw driving, even under such high state uncertainty? Now, just a second. And screw driving is used as a case study mainly because even now it is quite one of the most bottlenecked application where robots still struggle, especially in automotive and aerospace industry. Now, as I mentioned from our observation, compliance plays a huge role in this, with the robot compliance being the impedance control, and tool compliance mainly because of the passive compliance that the tool has because of the spring-loaded mechanism inside the tool itself. And we use all standard industrial tools in this case. And like I said, this is an interplay between mainly active and passive compliance. And our objective was to study this method in a more data efficient way. So we can't really just collect data randomly and then just train a neural network as is to understand the screw dynamics. What we wanted to do was collect data in the most data efficient manner, and then choose a modeling method that could encapsulate this complex interaction between the screw tip and the surface and characterize active and passive compliance. And that is where we use a more physics-informed machine learning methods, which deploys a method called as SINDI, which is termed as systematic identification of nonlinear dynamics of a system, where rather than given an observation, you learn what the dynamics model would be, you directly learn what the coefficients of the fundamental governing equations of the dynamics of the screw would be. So to clear that out, let's assume that you have certain state variables defined by x and control variables defined by u, and you have a group of candidate family nonlinear functions. Now, the main decision that you make as a researcher in using SIMD is what family of nonlinear equation does your system belong to, and that comes through subject matter expertise. In screw driving, we mainly figured that most of the screw dynamics would be defined by first order, second order sinusoidal functions itself. And that is why the candidate family that we chose in this specific case included polynomials of first order and second order and sinusoidal functions. And then what you're trying to do is you're trying to learn the weight matrix, which is this particular sign matrix of the family of functions, which gives you directly the fundamental governing equations. And the loss function that you're trying to minimize is you observe the dynamics data of the screw tip and you try and reduce the MSE loss. And to collect the data, what we do is we have a screw tip with a colored screw tip and a marker, and we generate the screw motion data. And just to clear it out, this is only used during data collection. When you do execution, you know exactly what the dynamic model of the screw tip is going to be. And once you have access to the dynamic model, you know how the screw tip is going to behave, and you can quantify the uncertainty in which your robot can perform screw driving. And to learn the screw tip dynamics, what we do is we combine variational autoencoders mainly to perform state estimation, and also for understanding a low-level representation of the action variables that you can take. And in SINDI, what we try to do is we take the force input, and we also take the end effector orientation, and then we try and learn the dynamics of the screw driving system that we have. And in addition to performing screw driving, when you're dealing with such high precision tasks, it is important to also detect failure modes. And in screw driving, we mainly come across three types of failure modes, which is cross-threading. When you have a severe misalignment where no matter what you do, the screw tip is not going to fall inside the hole. And then you have thread jamming. So over here, we use mainly LSEM-based method where we take sequence of data from force and images, and then we try and do classification in what type of failure mode could the agent be in. And once you have identified the failure mode, we retrieve the right failure recovery strategy that there is. And the results show high amount of success rate even at a hole uncertainty of 3 millimeters in position. And here's a video demonstration. You can see that we are basically demonstrating a task of maintenance where this robot first unscrews, and then you have second robot that prepares the part for a human expert to come in and replace the part. And once the human expert is done performing the maintenance operation, then you can again perform the screw driving operations and complete the maintenance task. And this proves how robot can operate under high uncertainty, especially in terms of state, and then lead to the maintenance being completed. And the key insights that I would like you to walk away with is that when you have agents operating in high manipulation uncertainty, it is important to use physics-informed methods that gives you an explainable model of the system dynamics. And interplay between passive and active compliance can enable robot to again operate in a high uncertainty manipulation mode. Before I move forward, I just want to make sure that everyone can still hear me and I'm well connected. Hello?
Yes.
Yeah, all right.
Yeah.
All right,
I can hear you.
because I don't have a feedback right now because I'm seeing my screen, so I just want to make sure that whatever I'm talking is being conveyed. All right, now that we have seen how agents can operate under uncertainty, what we would like to see is how we can use physics-informed AI to actually detect different types of anomalies and failures, especially when it comes to deformable objects. Now, we've seen deformable objects in different type of tasks. We saw a robotic composite layup, and then there are deformable objects even in fulfillment industry. But these defects can be quite detrimental, and it's not about just detecting defects, but it also about detecting certain anomalous configurations in which these defects can exacerbate and then lead to a complete scrapping of the part. And that is where we take motivation for composite layup. And in composite layup, what one biggest issue that you have is that generating data of failures and defects can again be quite expensive. So the objective in this particular project that we wanted to do is, can we use physics-based simulation and advanced AGI techniques to actually generate synthetic data of defects at a large scale and then augment that large synthetic data with small amount of real data to learn a deep learning based image segmentation methods that can detect wrinkles and folds in a composite sheet. So the failures that we wanted to detect are shown in the images where we have actually conformed wrinkles, where you can see that the defect has already occurred. But as I mentioned, it's not just about detecting defects, but it's about predicting when failures will happen. And for predicting such anomalous lesion where you see these kind of folds that are being occurred, and these cannot be done using traditional CV methods. As you can see, if you use even any gradient-based methods, or if you wanted to do any sort of Hub transforms, or let's say you have any sort of feature detectors, point-based feature detectors that you want to use, they still will suffer and not generalize. And if the sheet appearance changes drastically, those methods fail quite a bit. That is where deep learning plays a great role, where it can generalize across different types of examples. But then deep learning again requires a lot of data. And that is exactly what this particular problem talks about. That how do we exactly generate a large amount of data by using physics knowledge of the sheet and using a physics-based simulation. Now, to do that, what we do is, initially, if you guys recall, what we tried to do in our initial work was to learn the deformation of the sheet and build like an FEA-based model of the sheet itself. And we have an in-house simulator called as the Vega FEM, which is a thin shell model of the composite sheet. And what it does is, given certain constraints and external forces, it simulates what the sheet shape will look like. Now, now imagine if you can combine this white-looking mesh, like cartoonish mesh, with some sort of texture or CGI, and then give it procedural texture and HDRI of the surrounding, then you can kind of output more photorealistic synthetic images. And now you're not limited by generating real-world data. You can use the simulation environment to generate synthetic data at scale. And the best part about generating this procedural texture at scale is you do not need to do manual data annotation. Since you have ground truth access to the simulation environment itself, auto annotation is also possible. So here is a comparison between synthetic images and the real images that we collected. The idea is to just capture the nuances of the images and not make them look, or not burn ourselves out on making them look highly photorealistic. And then we use a mask RSKNN based network, which is pre-trained on MS-Loco dataset. And we pre-train this entire backbone to do bounding box regression, semantic segmentation, and also we classify whether we have pixel-wise classification, whether a defect is occurring in a region or not. And what we saw was we could detect defects with a mean average precision of 0.98. where we use an intersection over union metric of zero point 0.5, which is standard across several image segmentation methods. And that is how what I would like you to walk away from this work is that you can use physics-based simulation to actually simulate failures, and then for robustness, use synthetic data at scale, but collect very small amount of real-world data to actually detect failure modes. And this makes your entire robotic system robust to failures and make your agent resilient, such that it can not only detect defects, but also predict when failures are going to happen. And then your policy can take this as a feedback and then improve upon it. Now, recently, what we've been trying to do, moving to a different set of work, recently what we've been trying to do is humans are quite adept in manipulating deformable objects because we have two hands. That is why we mainly use bimanual form of manipulation. So what I would like to now discuss is where bimanual manipulation can be quite useful. Now, in fulfillment industry, if you see, what earlier used to look like just rigid boxes is now turning into deformable packages, mainly due to increase in consumerism, and we're all guilty of ordering online in small batches, and that is why such small deformable packages are becoming more and more prevalent, and that is why it is becoming important for robots to actually learn how to manipulate such packages and perform bin packing. Now, our objective in this work was perform a bin packing task such that you can pack these totes with such deformable packages, such that you can take this tote from one end of the fulfillment center to the other end and still achieve the daily target of performing such a task. Now, motivation for using bimanual cell comes from how humans perform these tasks. As you can see in this video, what we do is we pick up a package and we coarsely drop inside, while one hand remains inside the bin and make sure that the packages are upright. And if you think about how you pack your suitcase when you travel, that is exactly how we do. We use one hand to stabilize the things which are already inside or create space, and then the other hand shoves the object inside the thing. And then that is how we achieve tight packing and also stable packing. And that is where bimanual shines. And bimanual shines not only in that, but also in avoiding failure, where if you just have one robot doing the task, or if you keep the other robot outside the bin, you can see that recovering from failures becomes quite difficult. While on the other hand, if you use the configuration which I just mentioned, one robot drops the package inside the bin, while the other makes minor adjustments, and then these robots can keep on doing this task over and over again and fill up bins such that you achieve the desirable packing. Now, the problem formulation for this particular setting is quite straightforward. Given a state, given certain observation of the state, which is RGBD image in this case, what you try to do is you do state estimation, and then you have a policy network which predicts your actions for both the robots, and then in the end you do perform bin packing. Now, there are several ways in which you can do this particular task. But what we found out that the main objective over here is that you're trying to find an optimal action which maximizes bin packing efficiency. So we take an inverse approach in this case, where we have this particular action prediction framework. Now, there's a lot to unpack over here, so let's walk through this one by one. Now, given a raw RGBD image, you have a bin state extractor which gives you the state of the bin, and you have actions of the two robots, which is robot 1, which picks and places the package, and robot 2, which does minor adjustments. And what you're trying to do is you're trying to improve the packing of the bin, and then each of the robots have their individual effects on the bin packing. That is why you have a packing score for robot 1 and packing score for robot 2. I would not go into detail what this packing score is. If you're interested, you can read the paper, which is available on my personal website or even on our lab website. And then, given these packing score, if you learn a forward model that gives you, for a given bin state and action pair, what the packing scores will be, then you can solve this inverse problem by deploying an optimizer in the loop. And then for a given bin state, what you're trying to do is you're trying to compute actions in an inverse way, which maximizes the packing score. And in the end, we kind of compute actions for both the robots such that your packing score is maximized. And in addition to that, and even in this case, we use deformable object simulation in Mujoko. And what we found out is that rather than randomizing the entire thing, uh, and one thing is when you're using simulators, there's always a sim-to-real gap. And what we found out that rather than just doing simple domain randomization and adaptation, we can kind of simulate failure modes and then use that failure mode data to do some sort of contrastive learning where the robot is learning a policy which understands what are the actions not to take. And then using that data, which is informed on the physics of the failure, what we found that sim to real transfer can be quite seamless and quite reduce the data requirement in this particular case. And here is a system demonstration where we use raw RGBD data and force information to do packet state estimation. And for a given bin state, we predict certain actions. And this sequence keep on going till we have a well-packed bin. And you can see that the robot keeps on adjusting the packages until and unless they are in a desirable location. And in the end, we have a tightly packed bin, and that leads to a particular downstream task. And the key insight that I would like to for you to walk away with from this work is that bimanual manipulation can open up a lot of opportunities, especially in more complex kind of tasks. And simulation, rather than just learning the good actions, you can use simulations to actually simulate failures and then teach a policy to a robot on what not to do rather than what to do. And learning from failures can lead to much more robust and resilient policies. So, in conclusion, what we have accomplished from this particular line of work that I presented is that using different types of methods, we understood different types of physics-based constraints. We understood how to enable robots to perform high-precision tasks, and then how to inculcate task-based constraints from human expert, how to enable robots to operate in highly unstructured environment, and how to enable them to detect failures, and not only detect but predict failures and make them resilient. And all of this was done by kind of smartly integrating intuitive physics with modern data-driven methods. And is that basically, does that solve all the problems and is deformable object manipulation solved? Well, I hope not, because I hope most of you are interested in this kind of problems, and there's a lot of problems that need to be tackled. One of them is, can we generate physics-based simulation that capture properties for large deformable objects and effect of compliance on the object dynamics? What I showed was basically 3 feet by 4 feet sheets. But there are several applications that have much larger sheets and much larger deformable objects. Then not just that, but can we basically learn human sequencing policies not just for a task, but also for manipulation? And can we perform manipulation and planning for different types of tasks and different types of deformable objects? And can we basically teach robots policies which understand the effect of their actions on the surrounding? That is the main research question that we want to keep on pursuing, and that is what I'll be pursuing for the rest of my PhD as well. And moving on, the main contributions of this work is that how we use physics-informed modeling for deformable objects. We saw how we can integrate advanced learning frameworks to actually directly learn the governing equations of a particular dynamics of the object. And in addition to that, we understood how we can make robots resilient to predict failures and recover from them. Because the key message that I want to for you to walk away with is that using these right physics-informed tools is quite important. Now, most of you have been hearing a lot of words such as foundation models and large models that are there. Now, those are great. Now, if you want robots to do very generalist tasks which do not require precision and safety is not that important, foundation models are definitely something to explore. But when you want robots to perform high precision manufacturing tasks where safety is of utmost importance, using physics-informed tools and using physics-informed methods and augmenting data-driven methods with these physics-informed tools is quite important, because there are several tasks right now in the industry where humans are still doing them, and they should not be doing them because they pose occupational hazards to them. And if you want robots to solve these problems, remember that physics-informed is the key. And I'll take any questions that are there now.
Thank you very much. Very inspiring. I'm curious about one specific scenario where the deformable object may not be, I should say, the elasticity of the deformable object probably is not known yet. So, have you ever tried to maybe use a robot to pinch or kind of have a soft touch of the object to kind of get a feedback sensing so that the robot can realize, okay, what exactly physics model I should use to best manipulate the object. Have you handle something like this?
Yes, I mean that's a good question. So one thing for sure is in the package manipulation work that I showed, which let me just go back here. So if you can see, when the robot is actually interacting with the package,
Yeah.
there's a force plot that comes in,
Mhm.
right? So what we're doing is we're using wrench and torque information to do package stiffness estimation. So that is one of the things where we use online sensing modalities to actually do state estimation for the package, where the deformability of the package, where the stiffness is kind of a surrogate to the deformability of the package. And then based on that, what we try to do is rather than selecting the model understands that if the stiffness is a belonging to a certain range of value, what are the right actions to take for the system. So that is what I've studied until now. However, let's say you have like a library of models, and given certain material parameters or physics parameters, what is the right model to choose? That's a different method that one could definitely use, but that is not something that I've done. What I've done is use these kind of uh, parameters, and that stiffness becomes, or the physics parameters becomes like one of the parameters for the model, and the model outputs the appropriate action.
I see. Okay, sounds good. Um, may I ask the classroom, is there any questions from the students?
Yes, there's a question.
Yep.
Hello. I want to add, when robot learn from demonstrate is using videos to learn.
So in this specific example, we did not use videos. It was humans. If you see let me go back to the specific slide so that it's clear. I think it's this one. So yeah, and if you see the expert demonstrating, they have like a handle tool. And if you see, there are these markers on top of it. So we use motion capture mainly. And then not just that, but in the handle tool, we have ingrained like a force sensor. So that gives you the force information. In this specific task, all you need is the sequence in which they are performing. And the sequence is extracted from the trajectories timestamps that we have. And you can see in ROS, we can replay the trajectory. So if you see the top left corner over here, we can replay the trajectory in ROS and you know exactly which lesion was processed at what time. So that is how we collect the demonstrations from the expert. But one could use videos as well. There's a lot of information, like there's a lot of work done which uses videos for doing LFD. So yeah.
Thank you.
Very nice.
All right.
So, what was the new topic that you are working on? What's the latest?
So right now I'm more interested in teaching robots policies, not teaching, but basically learning policies or action policies mainly, which are conditioned on avoiding failure modes. So right now, most of the work that people have been focused on is that if you fall into failure, you have a recovery strategy on recovering from failures. But what I'm currently focused on is, can you kind of learn what other or can you kind of give the model a right inductive bias such that the action that it generates are conditioned such that you will never generate an action that will lead you in a failure mode in the first place. So that is what I'm currently working on.
Okay. So do you work on also collaboration between human and robot? For example, packaging the stack of packages, but one robot being a person.
So, I wouldn't call myself an active researcher in human robot collaboration. So, most of the applications that you saw,
Yeah.
that I showed, is mainly that human is just an expert who's providing demonstrations, but there's no human robot interaction that I study. But that is one aspect that definitely can help, especially in case of deformable objects.
Yeah,
But
I
me as
think
a
if you
researcher,
move on to that aspect, it's more challenging because human motions are very random, but
exactly,
the system could be quite useful for the real world scenario because
absolutely
in the factory they may not have multiple robots
makes sense.
and also more issues in safety.
Absolutely, yeah,
Very nice. Thank you so much, Omei.
yeah,
I think I will be visiting to USC eventually. I mean, I will be visiting USC again very soon. I hope somewhere next year. So I hope I can visit you and have a deeper discussion with you.
absolutely. Looking forward to that. Yeah.
Thank you so much.
All right. Thank you.
Thank you.
Okay, thank you, class. The class finished. Okay, bye bye.